In this video, we're going to talk about concavity and the second derivative test. Let's first talk about the definition of concavity. So let's say we have a differentiable function on some open interval. When we talk about a graph having a concave up or upward shape, that's going to mean that the f prime, so the derivative, at any point is going to be increasing. So these blue lines, their slope is going to be increasing in number. And if I talk about a graph that is concave down or downward, the opposite of what we just talked about is true, that the f prime or its derivative value is going to decrease. Another way to think about it is that I have concave up, it makes kind of a U shape, and concave down makes the opposite of that, so an upside down U shape. Here I have a function, so f of x, and the graph of its derivative, f prime of x. There's a lot of different things going on here. The first, what's highlighted in blue in the original f of x is concave down part of the graph. Notice that it makes that kind of U shape, and it's going to be green where it's concave up, and that exactly mirrors in its f prime of x, so its derivative. So where it's blue or where it's concave down in the original function, the derivative here is decreasing. And also, when it's concave up in the original function, the derivative is actually increasing in its slope. A couple other things you'll begin to notice as you do a lot more work with this stuff is that if you notice where this thing peaks or finds a max on its concave down shape is also an x-intercept in f prime of x. Also here, where it kind of makes that minimum or where it starts to go down and then shift back up is also an x-intercept on our f prime of x. And that's because if I was to draw a tangent line right here or right here, I would have a zero slope, which is why it crosses through y equals 0 right here. Just some food for thought for you. Next, let's talk about how we test for concavity. Now that actually has to do with the second derivative. So that's when you take the derivative of the first derivative of a function. So if the outputs, whatever interval your outputs have, if they are all greater than 0 for the second derivative, then that means that the original graph of f is going to be concave up on that interval. And the converse is true. So if I have the second derivative and on that interval all the outputs are negative or less than 0, then on that interval the original function f is going to be concave down. And a quick little remark here is that you could actually use that to say that f double prime of x is equal to 0, the second derivative is equal to 0. But note that that would create a line, and concavity is not defined for a line because lines don't have curves. So a straight line is neither concave up or concave down. Let's do a couple examples. The first one is for this function, f of x, to determine the open intervals on which the graph of this rational function is concave up or down. So, using the rule that we just talked about, I'm going to take the first and second derivative and set that second derivative equal to 0 and test the intervals in which that thing is going to be concave up or down. So first thing I do here is take the first derivative, which is in blue, and I needed the quotient rule here, and in order to take the derivative of our first derivative, I also need the quotient rule and the chain rule. So I work this out, I try to simplify it as much as possible. I'm able to distribute this negative 12 here, combine my x squareds as much as I can, pull out a 36 from the numerator. So this is my second derivative. And now what I'm going to do with that is set it equal to 0 so I can find the places where my concavity might change or any critical points I might need here. So I'm going to set that equal to 0 over 1. I can cross multiply. So the only 0 I'm really going to get is this numerator here. So I set that equal to 0. I'm able to factor x squared minus 1 to get positive and negative 1 for my x values where the second derivative is going to equal 0. So I'm going to test numbers in between and see what I get. So the numbers I tested were negative 2, 0, and 2. I plugged them into this function right here, so the second derivative. So I found my output less than x equals negative 1 to be positive, so that means that the original function is going to be concave up in this interval, and then in between negative 1 and 1 I found the second derivative of 0 to be negative, so that means that my original function is concave down between -1 and 1 on the x-axis, and then greater than 1, I found my second derivative output to be positive, so that means that it's concave up from 1 to infinity. So using this information and double checking it with our original graph there for f of x, I can say that f of x is concave up, where x is from -infinity to -1, not inclusive, and from 1 to positive infinity, also not inclusive, and it's concave down, where x is from -1 to 1, non-inclusive. Now let's work through another example. So we are looking for the open intervals in which the graph of this rational function f of x is concave up and concave down. We're going to work through the same process as the previous problem. So I'm going to find the second derivative, set it equal to 0, test numbers in between, and figure out where this thing is going to be concave up and concave down. First thing I did is I took the derivative here, and then I took the second derivative, so I needed the quotient rule and the chain rule in that respect. And I simplified everything down. I skipped some simplification steps in here, but I'm sure you can fill them in. So for the second derivative, I end up with this rational function here. And I notice in the bottom that if I were to factor this out, that if I put positive or -2 into that denominator, it's going to zero it out. So x cannot be positive or -2. Then I tried to solve for 0, set this thing equal to 0, and really all I needed was the numerator there, and I found that x squared is equal to -4/3, which is not going to give me a real answer. So these are the two numbers I'm going to be working with. So the next thing I did was draw my number line here, and I used my -2 and 2 and regarded that these things cannot exist in our function. So I tested numbers in between that, and I found that the more negative I got from -2 is going to be concave up because that result was positive. And in between, x equals -2 and 2, I got a negative result here, so that means it's going to be concave down in f of x. And then as we got more positive than x equals 2, that's going to be a positive result, so that means it's concave up. So that means that we have two intervals where f of x is going to be concave up, and our graph matches what we say here, and just that one interval where it's concave down. So all of that brings up this idea of points of inflection. So we may have talked about this already, but points of inflection on a graph of a function is where the concavity changes from up to down or vice versa. So here are some graphical examples. So I'm going from concave up to concave down, so that's a point of inflection. And same thing here. It's kind of hard to see, but that's concave down and that's going to be concave up. You can also test it with the first derivative if that's going to be more negative or more positive. And then here's another point of inflection where I'm going concave up to concave down. And if you're looking for the points of inflection, you can use the second derivative and find where that's going to be equal to 0 or where the second derivative does not exist. So now let's work out an example of looking for the points of inflection and discussing the concavity of this graph for f of x. So what we're first going to do is take the first derivative and then the second derivative, set that equal to 0, test some intervals, and see where we can find our points of inflection. So I found my first and second derivative. I set that equal to 0. I find that my second derivative is going to be equal to 0 at x equals 0 and x equals 2. So those are my critical points here that I'm going to test in between, and I do the same thing as I did in a lot of different problems that we've already done, and I find that this f of x is going to be concave up from -infinity to 0, not inclusive, and then pick back up to be concave up from 2 to infinity. So that's what I have here in this graph, and then it's going to be concave down in between those 2 points, so between 0 and 2. So that means that my points of inflection are at x equals 0 and x equals 2, much like what I have here. So I just plug in 0 and 2 into my original f of x to find the y outputs. So the points of inflection are 0, 0, and 2, -16. And now I'd just like to take a moment to make a quick note about points of inflection. So we talked about our last theorem 3.8, which told us that at the second derivative, if it equals 0 or if that second derivative doesn't exist at a point, then that is a point of inflection. But the converse of that is not always true. So what that means is it's possible for the second derivative to be 0 at a point, but not be a point of inflection. So that may not be earth-shattering news to you, but it does happen sometimes. So for example, if I have this graph here of x to the 4th power, when I take the second derivative and set it equal to 0, x equals 0 is a solution to that. But that's not a point of inflection because this thing doesn't change concavity. So just a quick note on that. The last major topic I want to cover in this video is the second derivative test. And what this rule generally says that if I have a function, I can take the first and second derivative and they both exist, that the second derivative at some point c, and if that's greater than 0, like we've been testing for concavity that is, then at that point it's going to have a relative minimum at c comma f of c. And so the converse is true. So if I have the second derivative at some point c and that's less than 0, remember that concave down test, then the original function has a relative max at c comma f of c. So if I have that second derivative at c equal to 0, then the test fails. What that actually means is that f may have a relative maximum, a relative minimum, or neither. And so if that does happen, just use the first derivative test. And now let's work through an example of that. So let's find the relative extrema of this function f of x. Since this problem is asking for relative extrema, which is something that we haven't quite been asked for yet in this video at least, I'm going to take the first derivative and I'm going to set that equal to 0 to find my critical numbers. And I find them to be x equals 0 and x equals positive and negative 1. The next thing I'm going to do is take my second derivative, and all I do there, I don't set it equal to 0. What I'm going to do is I'm going to do my second derivative kind of test. I'm going to do those numbers that I found here, the critical numbers. I'm going to plug in negative 1, 0, and 1 into the second derivative and see what I get as far as the behavior goes. So I get a positive result from x equals negative 1, which means that that's a relative minimum. And then at f double prime of 0, I get it to equal 0, so that's nothing. And then the second derivative at x equals 1 gives me a negative answer, which means that I have a relative maximum. So these are my extrema. My relative max is at 1, 2, and my relative minimum is at negative 1, negative 2. And that's going to do it for this video. Thanks for watching.